So today I'm doing question 53 on page 114 of the physics textbook. So we will start off by merely doing section A of this. So section A states we need to draw a free body diagram for each block. Now, I'm assuming you've already read the question, but if you need to know any more information, basically the positioning between these two boxes right here, let me draw like a diagram of it. This is the 2, this is the 3. The positioning between there has a kinetic friction, so Kf, that is equal to 0.3, which you will need to know for block 2. And this area underneath over here is frictionless. So we don't need to worry about the area underneath the block 3. So now we can draw a free body diagram because we should be able to figure out everything else from here. And you know what? I may actually move this one down just a bit because it will make it easier to write. So, free body diagram. Well, let's first focus on the individual components. Um, we know that we'll start with the 2 kilogram weight, which is situated on top of the 3 kilogram weight. So we know that we have mass and gravity associated with this. We also know our normal force, the normal force up here. We also know we have a normal force since we also have gravity. There is a tension. There is a tension over here, tension 1. That is, let me see, tension 1 here is the same as tension 1 there. And then we also have the friction force that's going against that tension. That is, we'll leave it at FF. It's the friction force, kinetic friction. That's 0.3. That's 0.3 multiplied by some type of force in newtons that we haven't figured out yet. So the easiest way to start off here is that, well, since we know the mass of the object here is 2 kilograms, we can multiply that by the gravitational constant of 9.8 meters per second squared, which we will get approximately 18.6 meters per second. We can. It would be easier if we would round this, and that's how I would do it. But for the sake of consistency, we will just leave it as it is. We won't round the 18.6 value. So, okay. So we have this will equal. So now we have the force in newtons. Oh, sorry, I made a mistake here. It's not. It's not that. It's the force in newtons. So now we have the force in newtons. So now we have this technically becomes 0.3 multiplied by 18.6 newtons. This will equal about 6 newtons. I'll round to the nearest whole number just to make it look nice. So it's about 6 newtons. So we've been able to find the gravitational force. We now know that this force right here is 18.6 newtons. That means the normal force on the other side is also equal to 18.6 newtons. So if you take away, these are the important bits of information we have here now. So that would be our first free body diagram, and I'll draw it again later to make it look nicer. Okay, let me move this down so we have more room to work with. So now we have a 3 kilogram weight. We're just going to repeat the same step again. So we have a mass multiplied by gravity. Again, we have the normal force. And then we have a force here, but it's not friction, because remember, the surface underneath, as we go here, that's written in red, is frictionless. So it's frictionless. So since it is frictionless, we have no friction. So this is just tension 1, as seen in the picture. Then on this side, we have, oh sorry, this is not tension 1. What am I doing? I'm mixing up my numbers. This is tension 2. You have tension 1 on this side too. We will get to that. We will get to that in a bit. So as we know, we have a mass here. So let's just do what we already know. 3 kilograms multiplied by 9.8 meters per second negative squared. That gives us about around to 30 newtons. But remember, that is not all, because not only do we have the mass and gravity of the object itself, but remember, if we revert back to what is seen here, the object, the 2 kilogram object, is sitting on the 3 kilogram object. So the 2 kilogram object is sitting on the 3 kilogram object. So we also, for the 2 kilogram object, we didn't have to worry about, because the 3 kilogram object is not sitting on the 2 kilogram object, but the 2 kilogram object is sitting on the 3 kilogram object. So we have to factor that in because it's weighing it down. So not only do we have the mass and gravity for 3, so I'm going to put a 3 right here. I'm going to put a 3 right here so we know what we're doing. Not only do we have one for 3, but we also have a mass multiplied by gravity constant for the second block as well. So this would be in total 30 newtons, and since we calculated the newtons up here, I highlighted to be 18.6, I'll round that to 20. We'll round that to 20 newtons. That is approximately 50 newtons of force in the down direction. Which means the force in newtons going up, the normal force, would also be 50 newtons. Alright. That's not all, so we have tension, but we also have one more component in this problem. Because if we look at here, and I'm trying to explain this in a way that makes sense, I'm going to erase some of the things here. So we have also resistance here. Now resistance, remember, is not the frictionless surface, but this constant right here. Because when this block is being pulled down by this one, it also has to rub against the friction here, which remember is 0.3, the kinetic friction here. So since it has to rub against, I have to make this really fine, this area right here, since they're rubbing against each other, not only does the 2 kilogram object have a sort of friction, but in technicality, this rope right here also has this rope technically binding the 2 kilogram object to the 3 kilogram object. That rope also has a resistance. That rope also has a resistance. And we already know what that resistance is. The frictional force is equal to 6 newtons. So I'm just resizing it here. There you go. It's also 6 newtons. You know what? I will write that a little bit better. It looks a bit messy. The frictional force is also 6 newtons. So that's our 3 kilogram object. That's the free body diagram for that one. And then also here for the 10 kilogram object, which I will move once more. So that's not what I wanted you to do. That's not what I wanted. There you go. We'll just do that. Then we will grab this. Try not to get anything else, that's the problem. Okay. We also have a 10 kilogram object. Now this is the easiest one by far. This is the easiest one by far. So all we need to do is that we know from over here that there's a tension 2. I'll erase all this information again. We know that there's a tension 2 for this one. So we know there's a tension. Then we also know that there's a weight. We also know that there's a weight of mass multiplied by gravity. There is no normal force because this object is free floating. It's in the air being held up by that tension. So basically this becomes tension 2, which we still need to find in part B, and mass multiplied by gravity. Now I'll just do it here, 10 kilogram multiplied by 9.8 meters per second. We're going to round that because that's just 98. We're going to round that to 100. Just for the sake of simplicity. If you really want to go in depth, and we will still get the same answer as the book. But if you really want to go in depth, you can just multiply 100 by 9.8, and you'll get 98, and you can do the problems from there. But I don't think you need to do that because it's more work, and you still get the same answer. All right, I'm going to go on to part B now. We're going to go on to part B. I'm going to draw like a little line here and a little line there. Part B. So now we have to draw for each. So now let's remind ourselves what part B is. Part B says determine the acceleration of each block. Determine the acceleration of each block. So what does that entail? Well, that's basically using Newton's second law. That's basically what part B is. Part B is using Newton. Alright, just a small cut there. We're using Newton's second law to do the rest of these. So I'm going to do these by individual. I'll do them in different colors for everybody. Just maybe that makes it a bit easier. We're doing the two. There's going to be 3 different second laws that we have law equations that we have to write out. I'll write them out right now. Second, third, and 2 kilogram, 10 kilogram object, and 10. Okay. So I will just write this up so we have this as a reference. The sum of all forces in the x direction, because we only worry about the x direction here. I mean, the y direction was useful for finding the friction, but other than that, we don't really need to worry about that because we're worried about tension. We're worried about tension. Okay, so let's go back and think about this for the second one. For this 2 kilogram object, let's go back and think. So, we know there's tension one way, so we'll write this in blue. We know that there is a tension. We know that there is a tension, and we know from that tension there will always be 6 newtons of friction. So this is what we know. All right. So this basically gives us this component. So we know that this component right here, let me get to that, is the chain f of x. It's equal to t1 minus 6n, and it's equal to mass times acceleration equal to 2a. That's it. That's the first one. Let's do the third one. Force of x equals, well, this is different. This is different now because not only are we being pulled in this direction, not only are we being pulled in this direction, T2, the 10 kilogram object that's down here, is pulling on here. So from this, we have to subtract T2 minus T1. And not just that, since you're being pulled in this direction, we also have to subtract, remember, the kinetic force of friction. Basically, we have to subtract all of the object over here in the x direction. Because we have to include this object since they are bound together by this rope, tension 1. So we get tension 2 minus tension 1 minus 6N is equal to 3A. 3A because the mass is 3 kilograms. Alright then, so we're going to do that. Change in f of x. This one is actually a lot simpler than that because it's just gravity. This right here basically is replaced by mg minus T2. We all know mg is. I'm not going to go back to that one. It's basically 100 newtons of force minus the tension 2 is equal to 10A. Okay, so now what do we do from here? How do we get our answer? Now that is a good question. That is a good question. I would pause and take a look at this because it is actually a bit interesting how this works out. But let's just look here. We have, oh, that's not a highlighter. This is a highlighter. We have tension 2 here, right? Negative tension 2, let's not forget that. And we have T2 here, positive tension 2. Then over here, we have negative tension 1 and tension 1. So what's interesting here is what we can do is cross out terms that cancel each other out. Okay, now you may say, well, why can you do this? Well, you can do this because it's all part of one system. Well, I'll call it a system, but it's all part of technically all part of one type of pulley. Because they're all bound together, that means the ropes affect each other, right? So, since the ropes affect each other, we can say that, well, if there is a certain type of tension here, if tension 2 is in this direction, we have a tension in this direction, these tensions can cancel out with each other because they will just keep the object in one place. So we're able to cross that out. Then what we have left is 100 newtons minus 12 newtons is equal to 88 newtons. And we can say 88 newtons is equal to, well, 15A. And we got that by adding 10 plus 3 plus 2. That's all the kilograms of the system. Then, well, you know that this is basically just basic math. Divide by 15, divide by 15. A is about 5.87 meters per second squared, which the book gives you, I'm pretty sure 5.7 meters per second squared, right? Wait, yeah, that book gives you that one. Pretty close, just rounding changes it a bit, but you got your answer there. If you were to be more exact, you would get the kind of around the answer for your book. That's question B. Now, just to clarify, this is the acceleration of every block. Since they're all hooked to one pulley, they have to have the acceleration. All accelerations have to be constant since they're all hooked together by a pulley. So there you go. This is the acceleration. This is the acceleration of every block. I cannot write. It's been a long day. Okay then. So that was part B. I am running out of space here, but part C is not that hard. It's part C, I'll go up. It says find the tension in the strings. Find tension in the strings. Well, there's two sections where we need to find the individual tension of the strings. We'll revert back to these force equals mass times acceleration equations here. Oh, oops. Okay, we cannot. There's one of these equations we cannot use, and that's because we're not able to isolate the tension, the individual tension strings. So that is a 3 kilogram object because here, since we have technically T2 minus T1 minus 6n equals 3a, we can't find the T2 and T1. So we basically, for this one, we ignore, for question C, we ignore the middle equation. Basically now it's just plugging in numbers. So we have to know, and I will write it down here again. We have to know that T1 minus 6 is equal to 2, and T2 plus negative 100 is equal to 10, 5.87 meters second, to 5.87 meters negative 2. And we got that, remember, from the acceleration of a block. We were able to do this because now we know the acceleration. Now we can find the tension. So since we're able to cancel out the tensions and find the acceleration, we now can find the acceleration. And we now can use the acceleration to find the tension of every object. So if we were to solve this out, I'm not going to show you how to use a calculator here, but basically it's T1 equal to 17.73 newtons, just about 17.73 newtons, and T2 is equal to 41.3 newtons. So that's basically the whole question solved. I'll review this one more time. I know maybe it's a bit confusing for some people. Actually, I would review. Hmm, let's go in this room. I'll just go over this. I'll go over this really quickly. I'll go over part A really quickly because I know that part is probably the most confusing part for a lot of people. And I said I would go over it, so I'm going to go over it. I'll leave certain parts that should not be too confusing. Okay. So for section 2, so for part A, I'm revisiting part A because I told you I would go back and try to explain this better. Part A, remember, we have tension because of the tension string right here. Pay close attention here. We have the tension string, so tension 1. Then on the other side, we have the friction force. So from what you know about friction multiplied by the friction constant multiplied by 20 newtons. 20 newtons we get from here. I just rounded 20 newtons because it's easier. The normal force is equal to about 20 newtons. This is about 20 newtons. So there you go. Basically, if you were to write this, it would be tension over here, tension 1, mass times gravity, 18.6 newtons going down in the down of the y direction. So negative y direction. And then you would write into the positive x direction. The 6, basically 6 newtons. This is equal to 6 newtons. You get about 6 newtons for the frictional force. Then up would be a 20 newton normal force. Then for down here, let me erase all the things we did. Then for down here, what you would write would be so you would write tension 1 pulling to the negative x direction, tension 2 pulling the positive x direction, the normal force. Remember this one is tricky because we have to also include 2 kilogram object. So the normal force would be 20 newtons of the 2 kilogram object plus 30 newtons of the 3 kilogram object equals 50 newtons. So the normal force would be 50 newtons. Then to pulling the object to the left, we will have a frictional force since technically this is pulling the object to the right. So frictional force is acting against the string. So the object 3 technically has sorry, object 3 kilograms technically has a frictional force applied in the other direction. So that's how you would solve that one. Then 10 kilogram object, tension 2, mass times gravity, 10 kilograms, 9.8 meters per second at 100 newtons. Then for part B, we went through this. We were able to cancel out, we were able to create the equations just using Fx equals mass times acceleration in the x direction. We don't need to care about the y direction because we're not being asked that. We were able to realize that we were able to cross out each individual tension. We're able to add two negative sixes together plus 100, and then add all the weights together by the acceleration. So to get 15a, we were able to get 15a. So we got 88 newtons is equal to 15a, and we were able to get the acceleration of each individual object, since they all have to be the same. Each individual block, or we can say that. Then we're able to find the tension by merely taking those Newton's second equations and plugging in numbers. And plugging in numbers, we're able to solve that. And we got our two final tensions, 17.73 and 41.3. Hopefully I helped you. Hopefully you can write and do this a little bit neater than I did. But hopefully I helped you to realize how to solve this problem. And hopefully you can go on and do other problems. Thank you for listening and have a nice day.